This video goes through the basics of mechanical power screw analysis. Power screws are simple machines for lifting loads. We can view a power screw as a variant of the inclined plane, a well-known simple machine. Inclined planes are used for raising or lowering loads. For example, pushing a load up a plane allows us to do some work, moving the load up. A screw can be viewed as an inclined plane that's wrapped around a cylinder. This allows us to lift a load using rotary motion. For example, on the right, we see a lead screw with a brass nut attached to a motor that drives the screw. As the motor rotates the screw, the nut will move up or down. Here's a video of someone else's 3D printer. Here we see a lead screw that is controlling motion in the x-axis, another one in the y-axis, and then there's a third one that can control motion in the z-axis, the vertical axis. Here's another application of power screws, a vehicle jack. This is a screw that has a series of mechanical transformations. So we have the power screw that is vertical, that lifts the vehicle or other heavy load up. The brass colored nut, we can see that rotates around the screw, but this nut is driven by a worm and gear, and that's another stage of force or torque amplification. Here's another example. Here's another vehicle jack that uses a power screw in a different way. It's a mechanical linkage that has a power screw in the middle, a lead screw. If we rotate this screw, it pulls the ends of this linkage together and causes the top of the jack to exert a force upward. So what are some properties that are desirable for power screws? Often we want to get a particular relationship between rotational and linear translational motion. We'd like to have power screws that are strong and durable. We'd like to generate usually a certain amount of force. We'd like to have power screws that are efficient, especially in cases when we're concerned about power transmission. Sometimes we'd like to know, can it be back-driven? For example, with the vehicle jack applications, we would really like a power screw that cannot be back-driven so that we don't need some other mechanism to hold the vehicle up. There's some additional failure modes to be aware of beyond strength. Buckling from axial loads if the power screw has compressive axial loads. And then whirling vibration from rotation similar to shafts if we encounter high rotational speeds. There are a few important types of power screws. The first is a lead screw. This has either square or Acme threads, which we'll look at in just a moment. These are low cost. They're fairly easy to manufacture, but they can have somewhat high friction, so they are less efficient than other options. An alternative is a recirculating ball screw. We have balls that roll through grooves on the screw, and this rolling action instead of sliding reduces friction. There are passages that allow the balls to leave the screw and then go back, hence the term recirculating ball screw. This is more efficient, the friction is reduced, but these are more expensive. These are the two main types of threads for lead screws. On the left, we have square threads. These are more efficient than the threads on the right. There's less energy loss if we use square threads, but these are more difficult to machine because of the square shape of the threads. These are good for high power applications because of their improved efficiency, but they are more expensive. Acme threads are less efficient because of wedging action and more complicated forces that we have between the threads of the screw and the associated nut. These are easier to machine, however, and are less expensive. Also, they have the advantage of being a bit stronger than square threads because they have a wider base at the root of the threads. Let's go through some basic power screw analysis. One thing we're often interested in is the torque required when turning the screw to raise or lower particular loads. the first step in this analysis is to draw a free body diagram for each case where we are either raising or lowering a load. And so the diagrams that we have here show the thread, imagine it unrolled from the screw, and then we can just analyze this as an inclined plane. So for example, if we have an object on this inclined plane and it's pushing down on the inclined plane vertically with this force F, then we can resolve the other forces acting at the point of contact with the inclined plane. So, of course, we're going to have a normal force that acts perpendicular to the inclined plane. And suppose we want to push the object up the plane, we're going to be pushing to the right with this load P sub r, or the force required to raise the load. But as we're pushing it up, there's going to be a force from friction resisting it. This is going to be F, the coefficient of friction, times the normal force, N. There are a few important things to define. The angle of this inclined plane is the lead angle. And the lead of the power screw is the vertical dimension of this triangle. And one way of thinking of it is the lead is how much will the nut move vertically when we turn the screw one rotation. F is the compressive force from the vertical load. As I mentioned before, P sub r, that's a horizontal force required to raise the load. And then if we look at the right, lowering the load is a bit different. If we want to move an object down this inclined plane, we're pushing from right to left with the force P sub L to move the object to the left. And this time, the friction force, F times N, this is still opposing motion. And so now it acts in the opposite direction. We're going to use this relationship, the torque being related to the load required to raise or lower the load, multiplied by the mean diameter divided by 2, or the mean radius. We're going to use this relationship to determine what is the torque required to raise or lower a load. Please note that this derivation ignores, for now, all other sources of friction in the overall system. There are some other sources of friction from rotational or sliding contacts in most power screw systems. Okay, we're going to go through a quasi-static analysis. That means we're just looking at the static forces. We're going to ignore any forces due to accelerating inertias. It's possible using the free body diagram for raising a load to derive this relationship. The force required to raise a load is equal to the axial force times the quantity sine of the lead angle plus the friction coefficient times cosine of the lead angle over the quantity cosine of the lead angle minus F times sine of the lead angle. If we are lowering the load, it's very similar. Now, if we apply this relationship between force and torque, we can derive what is the torque required to raise a load and what is the torque required to lower a load. There are a number of design questions that may be important to answer. One is, does a lead screw provide sufficient mechanical advantage for our design purposes? One way of thinking about this, if there's some maximum torque that we are able to exert on the screw, is the axial force generated by this torque high enough for our purposes? Another question is the ratio between rotational and translational speed appropriate for our needs? What are the design variables that influence these properties? The main design variables are the friction coefficient, which depends on the material type and the type of lubrication, the lead angle, and then the mean diameter. Something that's important for you to address yourself is to think through what kind of design insights can we derive from the relationships. For example, the equation shown below showing the relationship between the torque required to raise a particular load and these design variables. These are fairly nonlinear relationships, so some of it may not come from quick inspection. Another important question is whether the torque required to lower a load is positive or negative. So why would we be interested in whether the torque required to lower a load is positive or negative? If we have the case where this torque is less than zero, no additional torque is required to back drive the screw. Or in other words, the axial force that's being applied to the screw is enough to back drive the screw. So it's not self-locking. If this torque is greater than zero, then additional torque is required to back drive the screw. And we say that it is a self-locking lead screw. Self-locking behavior is critical for some applications. For example, the vehicle jack that we looked at before. We can determine whether the torque for lowering is positive or negative by looking at this formula. And if we look at the numerator of the second term, we can see pretty easily that's going to govern whether T sub L is positive or negative. So if pi times the coefficient of friction times the mean diameter is greater than L, that is going to give us self-locking behavior. And it's possible to show through fairly quick derivation that this is true if the coefficient of friction is greater than the tangent of the lead angle. So these two quantities, the coefficient of friction and the lead angle, are what govern whether a power screw is self-locking or not. Also, all of these derivations so far assume square threads. If instead you're using Acme threads, things get a little bit more complicated because of the wedging effect we talked about and the more complicated forces. And these are all addressed in your textbook, and variants of these formulas are given specifically for Acme threads. Okay, what influences friction? Experiments have revealed that the coefficient of friction is largely independent of axial load for lead screws. It's also nearly independent of rotational speed, but is influenced by lubricant properties. There is an influence of material combinations on the coefficient of friction. For example, we can use different materials for the screw and the nut. Here's a table from your textbook showing 3 different screw materials and 4 different nut materials and the ranges of the coefficient of friction that are typically seen with these different combinations. Another thing that we're interested in is reducing wear. One way of doing that is limiting the bearing pressure on the threads to prevent wear problems. So we're going to use this diagram to analyze what bearing pressure is. Here we're assuming the thread is horizontal. The bearing stress is possible to show is equal to minus 2F divided by pi times the mean diameter times the number of engaged threads times the pitch. So the number of engaged threads is how many threads are helping to take the load that are currently engaged with the nut. Here are some limits on bearing pressure for different combinations of screw and nut materials. Another thing we're interested in is the efficiency of power screws. Here we're going to look specifically at efficiency for square threads. That's equal to T naught over TR. So what's T naught? This is the torque required to raise a load if there was no friction, if the coefficient of friction was equal to 0. And then TR, that's what the actual torque is required to raise a load. And we can use this formula then to quantify what the efficiency of a power screw is. Looking at this is another case where it's important to think through what kind of design insights could you get from these relationships to help you learn how to design power screws to improve efficiency. Of course, reducing friction is going to improve efficiency, but what else might you change to improve efficiency? There is an additional source of friction that's important to be aware of, not just the relationship between the threads on a power screw or lead screw and the nut, but also a thrust collar. So if we're using a lead screw to exert a force, either in tension or compression, we're going to have some way of resisting that force, not just the nut, but the screw is going to have to be pushing up against something. And so we're going to use a thrust collar that's going to push against a structure that is supporting the screw. So this thrust collar resists an axial load while allowing screw rotation. There's going to be friction between the surface where there is relative motion between the collar and the structure supporting the screw. And then, of course, there's going to be an opposing axial force from the nut. And we can calculate this torque due to collar friction using this formula. So torque due to collar friction is equal to the axial force F times F sub C, which is the collar friction coefficient, times D sub C, the mean collar diameter. And this is shown in the figure to the right, what the mean collar diameter is. Okay, let's go through a few important power screw failure modes. One is yield of the main screw body. There are multiple stress components that you will need to combine using some failure theory, for example, the distortion energy failure theory. One component of stress is this shear stress in the main screw body due to torsion on the screw. And that shear stress, that's going to be equal to 16 times the torque present in the screw divided by pi times the root diameter cubed. Now, recall the root diameter, that's the diameter if we're measuring from the very base of the threads. Now, the next component is the normal stress due to axial load, and this can be either in tension or in compression. That's going to be equal to 4 times the axial force divided by pi times the root diameter squared. Another important failure mode is buckling due to compressive axial loads. Of course, if it's only in tension, we don't need to worry about buckling, but power screws could also be in tension. Often these may be an intermediate column, meaning, if you recall, that buckling is due not just to elastic instability, but also there's some yield going on. And so if we use the parabolic Johnson formula, we can predict at what load an intermediate column is going to buckle. And of course, that depends on the yield stress, S sub y, the length, the unsupported length of the column. And then the term on the right, we have 1 over CE, where C is the coefficient for the boundary conditions and E is the modulus of elasticity. One thing to note about power screws that's different from other things we've analyzed for buckling is that the unsupported length changes as the screw rotates. If the nut is helping to support part of the screw and prevent buckling, well, the position of the nut changes as we rotate the screw, and so L changes. Now, there are multiple things that contribute to the buckling of a power screw. One is a large force, and another is a long unsupported length, and we need to take those two factors into account and determine, well, what state of operation will this power screw be most likely to buckle under, and then use that to determine whether we predict buckling is going to occur. We finished recently the section on shaft design, and one of the failure modes was whirling vibration. And if we have a power screw that's rotating quickly, it also could be subject to whirling vibration. It behaves like a shaft. So whirling may result when power screws rotate at high speeds and if we have long unsupported sections. Another factor is how compliant in bending is the power screw. So if it's more compliant, then it's going to be more prone to whirling vibration. This is the simplified formula for the first critical speed for whirling vibration of a simply supported shaft with a constant diameter and no additional components on it. As with the buckling analysis, it's important to note that the unsupported length L changes as the screw rotates. And similarly, we need to evaluate the whirling first critical speed under the conditions that are most likely to exhibit whirling. And so that's going to be some combination of having a long unsupported length and high rotational speeds. And in some cases, maybe the rotational speed changes as the length changes. And so you're going to have to use your own judgment to determine what state is most likely to exhibit whirling. Also, with Whirling, be sure to have a look at vendor data sheets that you're obtaining your lead screw from to make sure that you observe all maximum speed requirements. Okay, let's have a look at stresses that are acting at the threads. And so here's the diagram again where we're simplifying the threads, and we look at the forces that are acting on these threads. And there are two primary components due to this axial load F. The first is going to be the bending stress at the thread root. So we can think of the thread as a cantilever beam. And with the geometry defined here, the bending stress at the thread root, that's going to be equal to 6 times the axial force over pi times the root diameter times nt, the number of engaged threads, the number of threads that are actively engaged with the nut, times the pitch. The second main component of thread stress is the shear stress at the thread root. That's going to be equal to 3 times the axial force over pi times the root diameter times n sub t times the pitch. Remember, as with the stresses for the main body of the screw, to use an appropriate failure theory such as the distortion energy theory to look at the overall stress state. Something to point out here is that we really have a statically indeterminate structure if we have more than one engaged thread. So if n sub t is greater than 1, this is statically indeterminate, and we're going to have multiple threads sharing the load, but not all threads generally are going to share the load equally in a statically indeterminate system like this. Design insights are one of the most valuable things that you can get from these activities. And so we want to address, well, what kind of intuition from the above models can you get to learn how to prevent things such as yield failure, buckling, whirling vibration, or excessive wear? Okay, now we're going to pull everything together that we've just covered and go through a quantitative example. This is the example from your chapter in the textbook that analyzes a power screw. And we're going to cover most everything that we went through in going through this example. So in example 8.1, we're looking at a power screw that's similar to this setup. We are told that it has a square thread, that the major diameter is 32 millimeters, that the pitch is 4 millimeters, that we have double threads, and this is something we've not really addressed yet. A double thread means we have 2 parallel threads wrapped in the helix around the screw, or in other words, if we rotate the screw 360 degrees, the amount the screw is going to move axially, that's the lead. But the lead in this case is not equal to the pitch because we have 2 parallel threads. So the lead is equal to 2 times the pitch. We're also told that the thread friction coefficient and the collar friction coefficient is 0.08, and the collar diameter is 40 millimeters. The axial load we need to support is 6.4 kilonewtons. Essentially, we're going to perform a complete analysis of this screw, except for whirling vibration. Part A asks us for a number of things. We need to find the thread depth, the thread width, the pitch diameter or mean diameter, the minor diameter or root diameter, and the lead. If we have a look at figure 8.3 regarding the standard geometry of square power screw threads, we'll see a diagram that looks like this. It identifies the pitch and a number of standard dimensions. We measure the pitch from the same point on two adjacent threads. The thread width and the gap between the threads is the pitch divided by 2. The height of each thread is the pitch divided by 2 as well. If the pitch is 4 millimeters, then the pitch divided by 2, the thread width and the thread depth, is 2 millimeters. Sketching this out to include both sides, this may help to visualize what the diameters are that we need to find. This is the major diameter, and we are told that it's 32 millimeters. This is the root diameter. And that is the mean diameter. The mean diameter, we can see from this drawing, is the major diameter minus the pitch divided by 2, or in this case, 30 millimeters. The root diameter is the major diameter minus the pitch, 32 minus 4, or 28 millimeters. The last thing we are asked to find is the lead. Now recall that the lead is the distance that the power screw or the nut travels axially for each full screw rotation. And this depends on whether we have a single threaded screw or a multiple threaded screw. If we define n to be the number of parallel threads that we have, in this case we have n equals 2. We're told that we have 2 parallel threads, or this is a double threaded screw. If we turn the screw one full rotation, we don't move axially the screw by just one pitch, but because we have 2 threads in parallel wrapped helically around the screw, we actually move the screw axially 2 times the pitch. So the lead is the number of parallel threads times the pitch, or in this case, 2 times 4 millimeters, which equals 8 millimeters. Now, we might ask, why would we have more than one thread on a power screw? Well, if we think about what's going on, we can have a pretty large lead, but with a small lead angle. Now, why would this be advantageous? Well, if we have a large lead, then it's a fast power screw. We have a lot of translational movement for a small amount of rotational movement. But why would a small value of the lead angle be important? Well, remember, the lead angle is one of the most important factors, along with friction, in determining whether a power screw is self-locking or not. This also has an influence on efficiency. Okay, in part B, we're asked to find 2 things: the torque required to raise the load and the torque required to lower the load. And this is a little bit different than we saw before, because we're accounting not just for the friction at the threads and the torque required to actually raise the load, but we're also going to include the torque required to overcome friction at the collar. So a modification of the earlier equation will include an additional term for the collar torque. This first term is the torque from the load and the thread friction. The second term corresponds to the collar torque. So we have 6.4 kilonewtons times 30 millimeters over 2. And just having a quick look at the units to see how these work out. Well, if we have 6.4 kilonewtons, and we convert that to newtons, we need to multiply that by 10 to the third. And if we have 30 meters and we want to convert that to meters, we multiply by 10 to the minus third. Well, those cancel out. That equals 1. And so we're going to end up with units of Newton meters. Then we have the lead, 8 millimeters, plus pi times the friction coefficient we were given, 0.08, times 30 millimeters, divided by pi times 30 minus 0.08 times 8. So that's the first term. Let's add the second term, 6.4 kilonewtons times the collar friction, which is the same as the thread friction, times 40 millimeters, all divided by 2. We calculate that out, and we obtain 26.18 Newton meters. That was the torque required to raise the load. We're not done with part B yet. We also need torque to lower the load. This is very similar. We're going to take the earlier equation and add the second term that corresponds to the collar torque. Okay, we're going to use the same unit management that we did in the previous calculations. I'm not going to show the details, but I want to point out a few interesting things about these two terms. So this first term is a minus 0.466 Newton meters, and the second term is 10.24 Newton meters. So what does this mean? Well, this first term, recall, that is the friction contribution to torque as well as the torque required to raise the load. And it's less than 0. So remember, if the lowering torque is negative, that means that our power screw is not self-locking, at least by itself, just looking at the screw itself. But there's more to the screw than just the interface between the threads and the nut. And so if we look at the second term, we have the collar torque, that's 10.24, that's positive. That's much larger than the negative torque for the first term. And we add these two together, we get 9.77 Newton meters. And with the nut thread interface and the collar taken together, this screw is self-locking. Part C asks us for the efficiency of the screw. We're going to look at the efficiency of the screw while raising the load. We obtained the torque required to raise the load from part B. And if we plug in all of the numbers, this is what we get. And just to make clear, as far as unit management, we get very similar cancellation that we saw in the previous part. If we calculate this out, we find out that we have an efficiency of 31.1%. Now we're going to move on to the stress calculations. These are a little bit more involved. First, we're going to look at the screw body stresses. We want to find the body shear stress and the body compressive normal stress. And one thing to note is that the torque required to raise the load is larger than the torque required to lower the load. And so if we're looking at, well, what are the largest stresses in the system, if that's what we're interested in, then we want to use this larger torque value for raising the load in these calculations. Okay, the body shear stress is 16 times the torque. Remember, we're using the torque required to raise the load over pi times the root diameter cubed. We get 16 times 26.18 over pi times 28 cubed. Now we need to pay attention to units here and make sure that we include any multiplying factors that may be important. So if we have a look at this a little bit more closely, well, millimeters cubed from the denominator here, that's going to be equal to meters times 10 to the minus third cubed, or meters cubed times 10 to the minus ninth. Well, that's also equal to meters cubed times 10 to the minus 6 times 10 to the minus third. Now, if we use these units, it's convenient. We'll end up with megapascals. And that means we're going to need this multiplication factor of 10 to the minus third. So if the 10 to the minus third is in the denominator, we can instead include a 10 to the third in the numerator. We calculate this out. We get a value of 6.07 megapascals. The next step is to find the axial normal force in the screw body. That's going to be equal to minus 4 times the compressive axial force over pi times the root diameter squared. That's going to be equal to minus 4 times 6.4 times 10 to the third newtons, since we have kilonewtons as our units, pi times 28 millimeters squared. And let's again pay attention to the units here. If we are looking at the top, we have units of newtons. If we look at the denominator, we have units of millimeters squared. Well, that's going to be equal to newtons over meters times 10 to the minus third squared, or newtons per meter times 10 to the sixth, and that is a megapascal. So we calculate these numbers all out, and we get a negative 10.39 megapascals. Now, we're working toward finding the total stress state for the system. The first step was finding the screw body stresses. Now we're going to start looking at some other aspects of stress. We're going to look in part E at the bearing stress, and then we're also going to look at the thread root stresses. So part E, we need to find the bearing stress. Now, earlier I mentioned that this is a statically indeterminate structure. If we have more than one thread taking the load, it's not going to distribute the load perfectly evenly across all the threads. And what has been discovered through experiments is that the first thread is what takes the majority of the load. And typically this is what we see. If we have thread number 1, that takes 38% of the load. Thread number 2, that takes 25% of the load. 3 is 18%. And experiments show if we go all the way out to a 7th thread, there's no load on the 7th thread. Now, if we're interested in where the maximum stresses are, it's really only the first thread we need to worry about. So one strategy that can be used that's described in the textbook just before this example shows up in the chapter is to look just at this first thread, assume that's where the maximum stress is, and set the axial force to 38% of the actual axial force of the thread. If it takes 38% of the load, then let's use 38% of the axial force and only look at the first thread. And then this also means that in the equations, we'll set the number of threads equal to 1, assuming we just have 38% acting at this single thread. So we get the bearing stress to equal minus 2 times 0.38 F instead of F over pi times the mean diameter times 1, the number of threads, times the pitch. Okay, if we plug in all the numbers, we get minus 2 times 0.38 times 6.4 kilonewtons divided by pi times 30 millimeters times 1 thread times 4 millimeters. And the unit management strategy is very similar to what we saw in part D when specifically we're looking at calculating the screw body normal stress. We calculate this out and we get negative 12.9 megapascals. Moving on to part F, we need to find the thread root bending stress. We can think of this setup as a cantilever beam but with annular geometry, and the formula for this is equal to 6 times 38% of the axial load. So again, here we're focusing in on the first thread that takes the majority of the stress, divided by pi times the mean diameter times 1 thread times the pitch. So we have an axial force of 6.4 4 kilonewtons, pi times 28 times 1 thread times 4 millimeters, and we get 41.5 megapascals. Now, this is a significant number. This is likely what's going to dominate the stress state of this system. And as we've seen in other components, bending has a significant contribution to stresses. Part G, moving on, we're going to look at the von Mises stress at the thread root. So what exactly does this mean? What are we looking at? Let me sketch out the thread root here. So we're going to have a normal stress in the screw body. We are going to have a normal stress due to bending, and that's going to be due to a moment. And then out of the plane here, we're also going to have a screw body shear stress. Some of these stresses are due to this axial force, and then also due to this torque. If we use a coordinate system labeled this way, X, Y, with Z out of the page, and I should point out that in the 9th edition of the textbook, at least, there is a typo. It says that Y is into the page, but it's actually Z that's into the page. Now, to help this be a little bit more clear and understand the stress state, I'm going to draw a stress element. This is going to be similar to figure 3.8 in your textbook, and we're going to be focusing on this critical point right at the root of the thread, at the top surface of the thread. That's where the bending stress is going to be the highest. So that's a critical point. We want to find out what is the stress state at that critical point. So let's look at Cartesian stress components on a stress element at that critical point. Okay, so what are some of the non-zero elements going to be? This screw body stress is going to be acting in this direction, and so that's going to be the normal stress in the y direction. The shear from the screw body torsion, that's going to be equal to the shear stress in the y-z direction. If we pay attention to the direction that the bending stress is acting, that will act on this plane, and that's going to be equal to the normal stress in the x direction. Now, all of the other stress components in this system are zero, so we really only need these three numbers to describe the stress state. Sigma y, that's equal to negative 10.39 megapascals. Sigma x, 41.5 megapascals, and tau yz is 6.07 megapascals. The remaining elements of the stress tensor are zero. So now we're asked to find the von Mises stress. So this is using the distortion energy failure theory. We need to go about doing a stress transformation to determine this. And if we look at equation 514, we'll get the following formula. Okay, I ran out of space at the end of the page, so all of those terms are under the square root. Now, a number of these things are zero, and so this formula is going to be simplified. Well, all of the sigma z terms are zero, and so those will cancel out. And then these other two shear stress values are going to cancel out. This simplifies the equation, and if we plug in all the values that we have, this is what we get. So the von Mises stress is 48.7 megapascals. Part H asks us to find the maximum shear stress value at the thread root. So recalling how to calculate the maximum shear stress value, this draws upon information from Chapter 3, and this goes back to calculating principal stresses. So we can see from equation 316, the maximum stress is going to be calculated using the first, the largest, and the third, the smallest principal stresses. Now remember the principal stresses, if we order them, sigma 1 is the largest, greater than sigma 2, and that's greater than sigma 3. Another way of thinking of this is to get the principal stresses, we rotate the coordinate system such that all of the shear stresses are 0. Now, keeping this in mind, that when we're looking at the principal stresses and the orientation corresponding to those principal stresses, all of the shear stresses go to 0. If we have a look at the plane that we drew earlier that involves the sigma x stress, well, the shear stresses in that plane, tau xy and tau xz, are 0. So what does this tell us? If tau xy and tau xz are 0, well, then sigma x must be a principal stress because that plane is oriented in a direction such that the shear stresses associated with that plane are 0. Now, just to verify this, we can go back to equation 315. This is the formula that helps us to determine the principal stresses for a general three-dimensional stress state. And this is a root finding approach. The three roots to this cubic equation are the principal stresses for a given stress tensor. Now, let's write this out and see how things simplify, and let's test this hypothesis that sigma x is a principal stress. If it is a principal stress, it will be a root of equation 315. Let's test that out. First, I'm going to identify that these three quantities, tau xy, tau xz, and sigma z, are all equal to 0. This allows us to simplify equation 315 significantly. Okay, we want to test if sigma is equal to sigma x. Will sigma x be a root of this equation? Now, the independent variable sigma shows up here as a cubic term, here a quadratic, and here a linear term. We're going to plug in sigma x wherever we see sigma and see if that in fact is a 0. Okay, let's multiply this out and see if anything cancels. Well, right away we can find that these two terms go to 0. Again, the next two terms cancel each other out. And again, the final term, or final two terms, those also cancel each other out. And so we have verified that yes, in fact, sigma x is a principal stress. So we don't know yet which principal stress it is. We don't know if it's sigma 1, 2, or 3. So we need to go through and determine the other principal stresses so that we can order them, and then we can use them in equation 316 to find out what is the maximum shear stress. So how do we determine the remaining two principal stresses? We're going to have to do a planar reorientation. We know sigma x, that's pointing in a principal direction, but what are the other two principal directions and the other two principal stresses? So this turns out to be a planar stress transformation, and we need to use an equation for plane stress. And if we go back to equation 313, this is exactly what we need to find the other two principal stresses. Okay, so it's going to be sigma y, sigma z, and tau xy that are contributing to the other two principal stresses. We can use this equation 313 to determine those values. I should point out that while the equation here says sigma 1 and sigma 2, we don't really yet know which one is sigma 1 and sigma 2. But this equation is going to give us two values, and then we can just compare them, rank them, and assign sigma 1, 2, and 3. First, we can note, well, sigma z is equal to 0, and so that's going to simplify things. And then equation 313 is going to result in the following. Okay, so we find that the two additional roots, the two additional principal stresses, are 2.79 and minus 13.18 megapascals. Now, if we go back and we compare that to the value for sigma x, we can rank them, and we can see that sigma x is the first principal stress, sigma 1, and then 2.79 is sigma 2, and sigma 3 is minus 13.18. Now, going back to equation 316 for the maximum shear stress, we can use these quantities to find it out. The maximum shear stress is 27.3 megapascals, and that's the answer to the final part of this problem.